In this video, we're going to talk about the photons. So everything about the photons. What is a photon? What is special size of photon? Photon is a name for the light quantum, and the photon idea is really crucial for our understanding of quantum mechanics. So this is essentially the minimum units for the physical quantum which we have. So I'm going to start compare what is described in electricity and magnetism. What is the light versus the quantum mechanically? In electricity and magnetism, the light itself described by two different fields. One is vertical electric field, the other is the magnetic field, which is over here. So they're perpendicular to each other. They're going to propagate it around the, let's say, z direction. So that's what is going to propagating. All the waves have wavelengths. So here I use a lambda to describe the wavelengths of the light, so which is over here. That's wavelengths. And of course, in the frequency domain, it's also frequencies, which we use the letter mu to representing that. And this is the classical description of the light. In quantum mechanics, we use a photon concept. Photon is just a particles. Particle must have a size. And there is no well-defined particle size for the photon. But commonly, we usually use the wavelengths of the classical way to represent this. So essentially, the wavelengths is comparable, the size is comparable to the wavelengths itself. So for instance, if I send out the one photon and the photon distributed, let's say elongated along the propagation direction, sometimes may be elongated along the lateral direction, depending on the photon source. So what kind of source you are using, the shape will be different because of this. And you're sending one at a time, and then you can detect them. Use the so-called single photon detector. So essentially, when you shoot one photon, it has a one click, and the room must be dark. Otherwise, the single photon detector is going to be saturated very quickly because of too many photons. What is interesting here is the energy comparison between the classical and versus quantum. Classically, the energy of the light wave is described 1 over c times epsilon 0, which is the permittivity in vacuum, and E sub f representing the electric field of the light, and so that's a squared. So this is the energy. The reason I use the letter F is because the energy is used on the photon side, so I cannot do using the same E again. But anyway, so this is the total energy for the classical ENM. Quantum mechanically, one single photon has h nu. Nu is the frequency. These two frequencies are exactly the same frequency. Because the frequencies equals c over lambda, so therefore these two are related to each other in the sense that frequency and wavelengths relate to the classical picture. If we equal these two together, and we get an equation. So this tells us how large the electrical field has to be. I simply used one example in the titanium sapphire laser, which is 800 nanometer around near infrared range. And so this is the equation that I calculate. So if I calculate the electrical field, and you can see electric field is very weak because a single photon is extremely tiny. And experimentally, usually you can put a lot of filter in front of it. So then you get these single photon pulse, so like that. And of course, you can also measure them in terms of single photon. So this is how we usually do. And let me stop here, and I want to create another video on the slightly different topic related to this. So I am going to end this now, and I hope you like my video.